Good evening, dear all. Welcome back to another session of physics. That is, we are explaining today thermal physics. You know, thermal physics, it comprises actually 3 chapters in our plus 1. We have a thermal properties of matter, and we have thermodynamics, and we have kinetic theory of gases. The 3 chapters together for our NEET examination, we may have 3 questions, that is sure, and may vary to 5 questions. So 3 to 5 questions, it's a big volume for a student that is preparing seriously for the NEET examination. So from a topic where there is not that much chaos or difficulties, so we are explaining questions one by one and the relevant theory of thermal physics. Today I am focusing mainly on the chapter thermal properties of matter, where we have to study about thermometry, calorimetry, and conduction, thermal conductivity related problems, and last the 3 important laws. You know, that is the Newton's law of cooling and Stefan's law and Wien's displacements law. This all we are explaining in this short time with questions. So please be ready. We are explaining now the questions one by one. So the first one, please see, look. Question 1. The question is that 80 gram of water at 30 degrees Celsius are poured on a large block of ice at 0 degrees Celsius. The mass of ice that melt is, that's the question. So here, you know, we can see that 80 gram of water, so you know, 80 gram of water is adding actually here to 30 degrees Celsius poured on a large block of ice. So when this water is adding to ice, we can say the temperature of water will decrease. It becomes a 0 degrees Celsius. By taking that temperature, ice starts to melt. So we know that is the principle of calorimetry. Heat gained is equal to heat lost. So we can say in this example correctly, the heat gained is, that is the heat required to melt ice. So we can say the heat released during the cooling of water. During the cooling of water, water is cooling from where? From 30 degrees Celsius to 0 degrees Celsius. That is equal to, that heat is utilized to melt ice. So we can say heat required to melt ice. Heat required to melt ice. So we know the formula. The heat released during the cooling of water equation, that you know, that is MC delta T is equal to melt ice, what is the heat required? MLF. You know, C of water, that everyone has to know. You know, C means specific heat capacity. Specific heat capacity of water is equal to 4200 joule per kilogram Kelvin. And you know, that is also equal to, in the calorie if you are saying, that is equal to 1 calorie per gram Kelvin it is. So that is the C value. And another important point, what is LF? LF is latent heat of fusion of ice. LF value, that is equal to 3.35 into 10 raised to 5 joule per kilogram. So, you know, and this value is also we can write in calorie, that is equal to, we can say, 80 calorie per gram it is. So we can substitute that values here now. M is there, that is 80. Here, you know, when we are considering that is, it's better we can use the gram idea. So we can say that here 80, and C value I am taking in calorie, so it is 1, and the change in temperature 30 to 0. So we can say that is into 30 is equal to, here the mass of, we can say that correctly, block of ice. So I don't know how much ice is melting. M into LF is there, that is equal to 80 now. So we can say here, look, this 80 and 80 cancels. So we are directly getting mass is equal to 30 gram, because I didn't convert that into kilogram. So the right answer is 30 gram. So we can say the option A, the right one, 30 gram. 30 gram, the right option. So that's the idea for conversion. So this principle is very important. Heat released is equal to actually heat required or heat gained, the principle of calorimetry. And now the next question, please see, look. Here in this question, look, 4 pieces of iron heated in a furnace to different temperatures show different colors listed below. Then which one has the highest temperature? White is given, yellow, orange and red is given. The very important point, that is Wien's displacement law, lambda m is equal to B by T, where T is the absolute temperature or temperature in Kelvin scale. So the maximum wavelength, or we can say the wavelength corresponding to the radiation having maximum intensity, is inversely proportional to temperature. Now we can say here, if you are considering the picture here, temperature is inversely proportional to wavelength. So if you are considering the 7 colors VIBGYOR, we know that is red has highest wavelength. So highest wavelength will have least temperature, because lambda is inversely proportional to temperature. So in this example, it's very clear. That is, here yellow, if I am considering in this one, yellow, orange and red is given. So I am taking yellow. We can say yellow has the least wavelength compared to the given colors. So yellow has least wavelength means it has a highest temperature. So which one has the highest temperature? Right answer is option B, that is yellow. Now we are explaining the next question now. So please see, look, question 3. What is question 3 now? Look, the energy emitted per second by a black body at 27 degrees Celsius is 10 joule. So we can say the energy emitted at 27 degrees Celsius is given. If the temperature of the black body is increased to 327 degrees Celsius, the energy emitted per second will be how much? So we know it's very important law. As I said before, we have Stefan's law. What is Stefan's law? That is the energy released from a black body per unit area in unit time is equal to, we can say, sigma T raised to 4 is there. It is proportional to the 4th power of absolute temperature. So here we can say, first case I am taking the energy now. So I can write the equation here, that is E1 divided by E2 is equal to, sigma is cancelling, we are taking the ratio T1 raised to 4 by T2 raised to 4 is there. Here first case temperature 27, when we are applying Stefan's law, convert Celsius into Kelvin. So I am converting T1 into Kelvin, 27 plus 273, so that is 300 Kelvin, and T2, that is 327 plus 273, that is equal to 600 Kelvin. So all values are there. I want to find E2. E1 is given, that is in the question 10 joule. So 10 divided by E2 is equal to, T1 is 300 raised to 4 divided by 600 raised to 4 is there. So that I can say 300 raised to 4 divided by 600 is, I can write 2 into 300 raised to 4. So 2 into 300 raised to 4 is there. So here 300 raised to 4, 300 raised to 4 cancels. It is 2 raised to 4 is there. So I can write 10 by E2 is equal to 2 raised to 4 is 16. So E2 is equal to 160 joule. 160 joule. So the right answer we can say that is equal to 160 joule is there. Take care, this point is very important. That is, the heat energy released or emitted or radiated from a black body per unit area in unit time is directly proportional to fourth power of absolute temperature. So E proportional to sigma T raised to 4, fourth power of absolute temperature. So that is why this law, Stefan's law, is important. Now we are explaining the next question. Look, see, a steel wire of uniform area 2 millimeters square is heated up to 50 degrees Celsius and is stretched by tying its end rigidly. The change in tension when the temperature falls from 50 degrees Celsius to 30 degrees Celsius is, Y value given and alpha value given. So how the extension related to Young's modulus and change in temperature? We know this question is relating the mechanics of solids, thermal properties of solids, and same manner the chapter thermal properties of matter. So first point, when Young's modulus, we have the formula Young's modulus, Y is equal to FL by A delta L. So I can write delta L is equal to FL divided by YA. In the same manner we have a delta L equation in the case of a thermal expansion also. We have a delta L is equal to alpha L delta T. So we can relate these two. So we are getting, FL by YA is equal to alpha L delta T. So this L and L cancels. So we are getting F is equal to YA alpha delta T is there. So this is actually the thermal force. And if they are asking in the question thermal stress, then we can say divided by A. So Y alpha delta T will be there. So all datas are given here. So Y value is there. That is 2 into 10 raised to 11. And area given 2 millimeter square. So we are converting that into meter. So 2 into 10 raised to minus 3 square. So it is minus 6 millimeter square. Then we can have a alpha value. Alpha value is there. That is 1.1 into 10 raised to minus 5. Then delta T. Delta T, it is heated up to 50 degrees Celsius and falls from 50 to 30. So we can say delta T is 20 degrees Celsius. Now we are simplifying the values now. So we can say here 2, 2 and 2. So it's coming 8 into 1.1. Then the 10 powers we are considering. Here there is 1 0 is there. And here 11, so 12 and minus 6 and minus 5, that is minus 11. So we can say 10 is coming. So 88 Newton is the right answer. So we can say right option is 88 Newton, option C. So I'm repeating once more. Please see, when a rod is heating and if it is not allowed to expand, the thermal force set up in that is YA alpha delta T, or the thermal stress is F by A, that is equal to, we can say that is Y alpha delta T will be there. Additional point we can note, the thermal stress equal to F by A, and that is equal to Y alpha delta T is there. So this is also very important relation for our upcoming NEET exam. So now we are explaining the next question. So look, question 5 we are explaining. So what is question 5? The volume of a metal sphere increases by 0.24% when its temperature is raised by 40 degrees Celsius. the coefficient of linear expansion of the metal is. So we can say here how much is the volume increased? 0.24 percentage. Volume increased when its temperature is raised by 40 degrees Celsius. So you know what is the volume expansion equation? We know that is delta V is equal to gamma V delta T is there. But the data given in percentage, so I can say delta V by V is equal to gamma delta T. So you know delta V by V is given 0.24 percentage. So 0.24 divided by 100 is equal to, now gamma into delta T is there raised by 40, so that is 40. So I can find gamma is equal to 0.24 divided by 100 into 40. And you know 0.24 means I can write 24 into 10 raised to minus 2 divided by 4 into 10 raised to 3. 24 by 4 is 6. So we can say 6 into 10 raised to minus 5 is gamma. But they are not asking gamma in this question. So please see, they are asking in the question what is the coefficient of linear expansion. So you know linear expansion is alpha. So I want to find alpha. If you have gamma, then how I will find alpha? We know the relation. Gamma is equal to 3 alpha. So alpha is equal to gamma by 3. So we can say 2 into 10 raised to minus 5 is the value for alpha coming. So we can say 2 into 10 raised to minus 5 per degree Celsius. So that's the question 5. Now we are trying question 6 now. See, look, it's a graph question. We know the variation of density of water with the temperature is represented by. So you know variation of density of water with the temperature is a very important idea. I think you have that idea correctly. That is anomalous behavior of water. Water contracts on heating from 0 degree to 4 degrees Celsius and then it will expand. So that is exhibiting by water, and due to that property, you know, the life existing on the earth. The anomalous property of water protects a large amount of animal and plant life, underwater. Water body starts freezing from the top due to actually this anomalous behavior. So how this variation of density with water structure? Now look, if I am sketching here volume temperature graph, then you know the graph will be like this. So water contracts on heating and its minimum volume will be 4 degrees Celsius. Volume will be minimum at 4 degree. Now if I am sketching the density temperature graph, then we can say the graph will be like this. So at 4 degrees Celsius, the density will be maximum. So this is the graph for density temperature 1. So the right option is option A. Option A, the right one for the density variation with the temperature. Anomalous behavior of water is a very important point. So now the next one we are explaining, that is question 7. A body takes, please see, 5 minutes to cool from 90 degree to 60 degree. If the temperature of the surroundings is 20 degree, time taken by it to cool from 60 degree to 30 degree is how much? You know, it is actually Newton's law of cooling. You know, we said there are 3 laws in this chapter. Newton's law of cooling. What is Newton's law of cooling? It states that, you know, rate of loss of heat. Just I am to recall, I am writing rate of loss of heat is directly proportional to the difference between temperature and its surroundings. So T minus T naught, rate of loss of heat is directly proportional to T minus T naught. You know, rate of loss of heat, if I am getting that mathematically, we can write dt by dt is equal to k into t minus t naught is there. Now see, the first question we are considering here. Look, a body takes 5 minutes to cool from 90 to 60 degree. So from the first data we can write the equations. Here dt 90 to 60. So change in temperature is 30. So 30 divided by time taken is 5. So the data given 30 by 5 is equal to k into temperature of the body. You know, temperature of the body means it is the average temperature. So we have 90 here, 60 here. So what is the average temperature? 90 plus 60 divided by 2. So 150 divided by 2, that is equal to 75. So to understand, I am writing 90 plus 60 by 2 minus surrounding temperature is given here, that is equal to 20 degree. So 20 degree. So I am ready to simplify this. 30 by 6 is equal to k into, here we can say 75 minus 20 is there, and that if you are simplifying, that is equal to 6 is equal to k into 55 is there, or k value we can find that is k is equal to 6 by 55. So that's the k value. Now I am using the same equation for the next case. For the next case, what is the equation given here? Time taken by it to cool from 60 degree to 30 degree. Time taken from 60 degree to 30 degree. So I want to write again the formula. So dt, here 60 to 30. So 30 only. Time taken, we don't know how much it is. K value we have 6 by 55 into t minus t naught. So here 60 plus 30, that's equal to 90. 90 by 2, that is 45. 45 minus 20 is there. Now that is 30 by dt is equal to 6 by 55 into 25 is there. So we can find dt. dt is equal to 30 into 55 by 6 into 25 is there. So we are simplifying that correctly. Now we can say yes, right. The right answer 11 minute will be there. You can simplify 30 and 6. So it is 5 coming, and then we can simplify here 55 and 25 is there. So divided by 5. So 50 by 5, 5 is equal to 11 minute is the right answer. So that's the point there, you know, a body takes, so this point is very important. Newton's law of cooling, where we can say that is, you know, look, the body dt by dt is equal to, yes, right, half is right, Sriveda right. Okay, now we have a dt by dt equal to k into t minus t naught, where t, how I will take t, that's the point. Many of the students are not taking that way, they will went wrong. T we are taking the average temperature 90 plus 60 divided by 2, and that is equal to, we can say, 75. So that's the right answer for question 7. Now we are trying question 8. So what is question 8? Please see. Temperatures of two stars are in the ratio 3:2. If wavelength of maximum intensity of first body is 4000 angstrom, what is the corresponding wavelength of the second body? You know how wavelength and temperature are related? Already we explained that lambda m is equal to b by t. So they are inversely proportional. So we can say lambda m, first one, so first star 1 divided by lambda m 2 is equal to T2 by T1 is there. So what is lambda? First the intensity 4000 angstrom given. Ratio here given 3 by 2 is equal to temperatures of the two star. So it is, I am repeating, please see. Listen here, look, lambda m1, suppose it is 4000 divided by lambda m2. T2 by T1 we need, but T1 by T2 given. So I am taking that is 2 by 3. So lambda m2 is equal to 3 into 4000 divided by 2, and this is equal to 2000. So it's coming 6000 angstrom. The right answer is, we can say, option B. Option B, the right answer is coming. So here the point, wavelength and temperature are inversely proportional. They are inversely proportional. Stefan's law, same manner. Wien's displacement's law, related questions. The second question that we are solving related to that. Now the question 9th. Question 9th is the question based on thermometry. Thermometry, there are conversion formula. Any thermometer we can convert in from any scale to any another scale. Sometimes a faulty thermometer given, how you will convert that into a new scale? We have the equation, T1 minus L of P1 divided by U of P1 minus L of P1 is equal to T2 minus L of P2 divided by U of P2 minus L of P2. This is the conversion formula for any scale to any other scale. So we can see in this question, a faulty thermometer has its lower fixed point, so L of P, marked as -10. And upper fixed point U of P marked as 110. So we can say correctly here, look, T1, see, if the temperature of the body shown in this scale is 62, so T1 is 62 given. Now we can say 62 minus L of P1 is -10, then divided by upper fixed point is 110 minus -10 is equal to temperature shown in the Celsius scale. Yes, right answer. See, temperature shown on the Celsius scale we want to find. So Celsius, we know that is, what is the lower fixed point of Celsius? That is 0 degrees Celsius. And the upper fixed point of Celsius scale is boiling point of water, 100 degrees Celsius. So we can say that is T2 minus 0 by 100 minus 0 is there. That is T2 divided by 100. So simplify 62 minus of -10, that is 72 by 120 is equal to T2 by 100 is there. So here this and this cancels. So T2 is equal to, we can say, 720 divided by 12 is there. So this is 6. So the answer will be 60 degree Celsius. So 60 degree Celsius is the conversion formula coming. So it's very important point, that is, when we are converting one scale to another scale, there is the conversion formula T1 minus L of P1 divided by U of P1 minus L of P1 is equal to T2 minus L of P2 divided by U of P2 minus L of P2. Any scale you can convert into any other scale by using this formula. Now we are explaining the next question. Look, question 10. Consider a compound slab consisting of two different materials having equal length, thickness and thermal conductivities K and 2K respectively. The equivalent thermal conductivity of the slab. So there is a problem for those they practice the question. Actually they may have a doubt, sir, here they are asking equivalent thermal conductivity, whether it is in series or whether it is in parallel. So it's understood, we can check both options because it is not mentioned here. So look, they are saying they have equal length and equal thickness. Equal thickness means we can say same cross-sectional area. Area will be same. We know that is when slabs are connected in series. What is the equation for equivalent thermal conductivity in series is equal to 2K1 K2 divided by K1 plus K2 is there. This is in series the equivalent thermal conductivity. Now we know if they are connected in parallel, what is the equivalent thermal conductivity? It is equal to K1 plus K2 divided by 2. In parallel it is K1 plus K2 by 2. In series it is 2 K1 K2 by K1 plus K2. So I'm checking now first one whether it is this option coming now correct. K and 2K. So K plus 2K equal to 3K. 3K by 2 it is not there. It is not there. So definitely it is not parallel. Now we are going to series. So 2 into K1 is equal to K. K2 is 2K divided by K plus 2K is there. So we can say that is here 4K square divided by 3K, or that is 4K by 3. So the right answer is 4 by 3K. So the right option is C. That is the right expression. See, this point is very important. That slabs can be connected in series and in parallel. Series equation, please recall, and parallel equation, please recall. This equation is possible if they have equal area, if A1 equal to A2 equal to A, same thickness. This equation is possible if they have same length, if L1 equal to L2 equal to L. So that's the point now. Now we are explaining the next question, question 11th. So what is question 11th? Please see, look. 5 gram of ice at 0 degrees Celsius is dropped in a beaker containing 20 gram of water at 40 degrees Celsius. The final temperature is, the point here, 5 gram of ice is dropped into a beaker containing water. So please, suppose I am considering that picture now. Here water is there. 20 gram of water. I am adding to that water, see, that is ice now. So what happened, ice will melt. And one more, the temperature of water will be decreases. Then ice melt water and the temperature of the water decreases and they attain a common temperature. So suppose I am assuming the common temperature, here it is T now. So we can say the picture correctly here, look. So we can say that when the 5 gram of ice is mixed with water now, water drops its temperature. So that is, we can say heat lost by water. Heat lost by water. That heat is utilized. Heat required to melt ice. Heat required to melt ice plus then this ice melt water, it has the temperature. Suppose we are considering ice melt water temperature is 0 degree. Then its temperature increases. So that is heat required to increase the temperature of ice melt water. So suppose I'm assuming the resultant temperature of the mixture is now T. So water temperature loss from 40 into T. So we can say here mass is equal to 20 gram. I'm again taking the calorie idea only. So C value 1 and it is 40 minus T. 40 minus T. Heat required to melt ice, we can say MLF idea. So we can say that the ice mass is 5 into 80 plus. Then heat required to increase the temperature of ice melt water. That is also MC delta D. So I can take ice mass is 5, but now ice is water. So I can say that is the specific heat capacity of water 1 and its temperature increases from 0 to T. So we can say it is T will be there. So I am writing now that is 20 into 40, that is 800 minus 20T is equal to here 5 into 80, 400 plus 5T is there. Take to this side. So 800 minus 400 is equal to 25T is there. So that we can say 400 is equal to 25T. So T is equal to, we can say 400 divided by 25. So 100 by 25 is 4. So 4 into 4, 16 degree Celsius. So we can say final temperature will be 16 degrees Celsius. I am explaining the problem once more. Please see, visualize what I am saying. Please look, 5 gram of ice. You are adding into 20 gram of water. So what is happening? The water temperature decreases. I am assuming that temperature decreases to T degrees Celsius. So water temperature decreases, water lost heat, so heat energy will be released. This heat energy is utilized to melt ice. When ice is melt, there is ice water. What is the temperature of ice water? 0 degrees Celsius. But the mixture has the temperature T. So ice water has to increase from 0 degree to T degree. So it requires the heat required to increase the temperature from 0 to T. So MC delta T formula there also coming. So we can say at 800 minus 20T, this MC delta T. This is MLF. So I can write the formula if it is MC delta T. Here MLF. Here also it is MC delta T. But this is ice. So that I am taking mass of ice is 5. Ice melt water currently. Now, how we got 5 into 80? Yes, 5 into 80 means, MLF. I will explain. What is 5 into 80? The heat required to melt ice. That is equal to M into LF is there. The heat required to melt ice. MLF. Okay, where M is mass. What is LF? LF, we explained before, in the beginning of this question correctly, latent heat of fusion we have, and we explained that correctly, please see, that is LF value we have the LF value, we wrote that correctly. LF is either in joule per kilogram or that is in calorie per gram. Okay, you got it. So, why I am using the calorie per gram here? Because, the data are given in gram. So it's easy. So I think you got it correctly. So we have the question 10th now, 11th completed and 12th we are explaining. Now look, an aluminium sphere of 20 centimeter diameter is heated from 0 degrees Celsius to 100 degrees Celsius. Its volume changes by, so that of coefficient of linear expansion of aluminum is given 23 into 10 raised to minus 6. Volume change, direct question it is, but calculation is there, numerical ability they are checking now. So what is the formula? The volume changes. So delta V is equal to gamma V delta T is there. Alpha, gamma is not given, alpha only given. So gamma is 3 alpha. So 3 alpha L into V delta T is there. So I can write 3 into alpha is 23 into 10 raised to minus 6. Volume of the sphere 4 by 3 pi r cube. So I can write 4 by 3 pi. Radius is 20 centimeter. No, diameter it is. So radius is 10 centimeter. Convert that into cube. So 10 into 10 raised to minus 2 the all cube. And change in temperature 0 to 100. So change in temperature is 100. So simplify. So we can say this 3 and 3 cancels. Now we are getting that. See, look, 23 into 4 pi into then 10 power only remaining. We can check now. 10 raised to minus 6 here. Minus 6 minus 2 into 3 minus 6. So minus 12. And then here 10 raised to 3 1000 and into 100, so 10 raised to 5. So we have a 23 into 4 pi into 10 raised to minus 7 it is. Minus 7. The multiplication is required actually. 23 into 4 pi is 288.8 into 10 raised to minus 7. So that we can write 28.8 into 10 raised to minus 6. See, why sir we are writing minus 6? Please dear, there is cc. Anyone know what is cc? cc means cubic centimeter. Cubic centimeter. You know, 1 cubic centimeter means 1 cc means 10 raised to minus 6 meter cube. So we can say 28.8 into 10 raised to minus 6. I can write that is 28.8 cc. So the right answer is 28.9 cc. So option A the right one. Option A the right one. So just numerical ability they are checking. Can you solve? That is equal to 10 raised to minus 12. How coming? Look, minus 6 here already. Look, minus 2 into 3. That is also minus 6. Yes, Sarim, you got it, no? Minus 6 here. Please see. Minus 2 into 3. That is minus 6. So minus 6 is minus 12. You got it. Okay. Now the next question we are trying, question 13. So please see what is question 13 now. A black body radiates energy at the rate of E watt meter raised to minus 2 at a high temperature T Kelvin. When the temperature is reduced to T by 2 Kelvin, what is the radiant energy? Same formula we studied Stefan's law. So we can say energy related. So we have the formula E proportional to. So E1 by E2 is equal to T1 raised to 4 by T2 raised to 4. So first case it is E. So I can write E. I don't know what is E2. I want to find. Temperature is T raised to 4. Second case T by 2 raised to 4 is there. So it's coming. That is equal to, we can say, look, E divided by E2 is equal to T raised to 4. Hereby T raised to 4. 2 raised to 4 is 16. Comes to the numerator. So we can say T raised to 4 and T raised to 4 cancels. So E2 I want to find. So E2 is equal to E by 16. E by 16. Yes, right answer. E by 16. Option D, the right answer. Yes, we were the right answer correctly. See, that is E2 is equal to E by 16. E by 16. Now we are explaining question 14. Question 14, I think you can answer. Direct question we have. Look, the linear stress developed in it. Linear stress developed. Young's modulus is given gamma. We know the formula. We derived F is equal to YA alpha delta T. YA alpha delta T. So we can say the picture here, stress they are asking. So yes, RM. So stress means F by A. F by A is equal to Y alpha delta T is there. In this question, instead of Y, gamma given. So we can say gamma alpha delta T is there, because instead of Y, they given in the question as gamma. Gamma alpha instead of delta T, T is there. So right option is option C. That is, see, question 14. The right answer is C. And now we can say the next point that we are explaining, question 15. Question 15, we practiced this question in our classroom. So you can solve it. What's the question? A metal rod of length 2 meter has cross-sectional area 2A and A as shown in the figure. The ends are maintained at temperatures 100 degree and 70 degree temperature at the midpoint of the wire. So we can say heat flows from where to where? Heat flows from this one to this, like this. There is heat current flowing. So the heat current flowing in this one and in this one are same. So I can say H1 and H2 are equal. So if the heat current, what is the formula for heat current? We know the equation. Everyone knows. H is equal to Ka into T1 minus T2 by L. They give the same material. So we can say same material means K value remains the same. So H1 is equal to H2. H1 and H2 are equal. So what is H1 now? K same. But look, area is here 2A given. You can see here the area is 2A given. So that is, I can mark that is instead of area 2A. The temperature, I am assuming this junction has the temperature. See, the temperature here I am marking that is equal to T. So we can say 100 minus T. So 100 minus T. Length is same 1 meter. Okay, equal to. Now the second case we can say that is H2. K will be same. Area will be A only. And T minus 70. T minus 70 by 1. So we are cancelling the terms. So when we are cancelling the terms, look, K, A cancels, K cancels. So we have a 200 minus 2T is equal to T minus 70 is there. Take to this side. So 270 equal to 3T. So we have a T is equal to 270 by 3 and that is equal to 90 degrees Celsius. So the right option is option C. 90 degrees Celsius is the right one and is coming 90 degrees Celsius. When they are connected in series, we can say when they are connected in series, heat current remains the same. Heat current formula H1, H is equal to K into T1 minus T2 divided by L. So the next question we are doing, look, 3 rods made of same material having same cross section are joined as shown in the figure. Each rod is of same length, temperature at the junction. Shortcut here, shortcut we are explaining. Identical rod, same dimension, same length, junction temperature easily we can find. The temperature will be 0 plus 90 divided by 3. So that is, we can say 180 divided by 3 equal to 60 degrees Celsius. Shortcut, see, recall. We solved it in the classroom. The question having different temperature area here. So look, different thermal conductivity. Our classroom question, here we have 3K, here we have 2K, here we have K. But it is not like that here. In this question, please see, look, all the rods have a same conductivity. So we can say all the rods have same conductivity, same material, cross section area same and length same. So we can say identical rods. So this idea we can try, that is the sum of these 3 temperature divided by 2. So that is equal to 60. Now question 17, look, question 17 we have very little time. So we can come back to that question. Before that we are trying question 18 now. Look what is question 18, please see. 2 conducting rods A and B. Conducting rod A and B of same length and cross-sectional area are connected first in series and then in parallel. Look, same length and cross-sectional area. In both combinations, a temperature difference of 100 to 0 degrees is mentioned. If thermal conductivity of A is 3K and that of B is K, the ratio of heat current flowing in the parallel combination to that flowing in the series combination is. So take care of this question. It's a trendy question that we are explaining now. Idea, please see, look, in the first diagram, please everyone see, first diagram, they are connected in series. We know if they are connected in series, we have the equivalent thermal conductivity formula 2K1 K2 divided by K1 plus K2. So we can say the K equivalent is equal to 2K1 is 3K. So we can say, and then K2 is K divided by K1 plus K2. So 3K plus K is there. So that is, we can say 6K square divided by 4K, or that is equal to 3 by 2 K is K equivalent in the first case. You know, in this question, it's very clear. They have same length and same cross-sectional area. So, what is the formula for the heat flowing? Heat is equal to, you know, Ka into T1 minus T2 divided by length. So, please, dear, look, for this two rod, you know, area same. Look, temperature difference is same for both cases. So, we can say T1 minus T2 same. Length also same. So, heat is directly proportional to K only. So, we can say that is the heat in the first case. So, you know, that is directly proportional to, so H1 first case by H2 is equal to K equivalent of 1 by K equivalent of 2. So, K equivalent of 1 by K equivalent of 2. So, K equivalent of 1 we calculated. Now, can you find what is K equivalent of 2 now? K equivalent, in the second case, what is the K equivalent? They are connected in parallel. In parallel, what is the equivalent thermal conductivity? K1 plus K2 by 2. So, we can say the equivalent thermal conductivity is K equivalent in this case. K1 plus K2. So, K into 3K divided by 2 is there. So, we can say that is 3K square. Here, you know, K plus, you know, what is the equivalent thermal conductivity in parallel? We studied K1 plus K2. So, we can say K plus 3K divided by 2 is there. K plus 3K divided by 2. So, that is 4K divided by 2 is there. So, the second case, it is 4K by 2. So, what is the ratio of heat? The ratio of heat. So, I am writing K equivalent 1, that is 3 by 2K. K equivalent 2, that is equal to 4K by 2. So, the terms we are cancelling. So, we can say K value cancels, by 2 cancels. So, we are getting that is equal to 3 by 4. The right answer, we can say 3 by 4. Correct that picture now. Here, you know, see, if there is any error, please make it clear. First of all, they are connected in series. So, equivalent is 2K1, K2 divided by K1 plus K2. So, we can say 2 into 3K into K by 3K plus K, 6K square divided by 4K, 3 by 2K. And the next case, they are connected in parallel. Parallel, it is K plus 3K divided by 2. So, that is equal to 4K by 2 is there. So, heat is directly proportional to thermal conductivity in this picture. Or we can say here the length will be added. And here, so we have the thermal equivalent thermal conductivity we have. So, how we can find the heat flowing now correctly? If you have doubts in this one, I will correct that. So, please see K equivalent we calculated. Then, suppose we are considering the heat current formula. I can check now what is the heat current formula will be there. Please see. So, I am just explaining from the beginning once more. Please dear look. So, you know, suppose I am considering this picture now. So, I think you got it. The first case and second case, we have the equivalent thermal conductivity here. 1 minute there. So, for those it is not clear, I am explaining that once more. So, please see, look. So, dear, please see, look, in the question now I am explaining the point here once more. First of all, series you got, that is the first case. In series, K equivalent is equal to, you know, that is 2 into, please see once more, 3K into K by 3K plus K is there. So, 6K square divided by 4K. So, that is equal to 3K by 2. Okay. Now, what is the heat generated in the first case? Heat in the first one, instead of equivalent thermal conductivity 3K by 2, K and area A, and we can say T1 minus T2 is same. So, 100 minus 0 divided by, but the length is here 2L. So, I can write that is 3K by 4L into A into 100 minus 0. That is the first case. Now in the second case, please see, you calculated the equivalent thermal conductivity. Equivalent thermal conductivity K1 plus K2 by 2. So 3K plus K by 2 equal to 4K by 2. 4K by 2. Then we have the heat flowing in the second case, that is equal to, instead of equivalent thermal conductivity 4K by 2, and then area here 2A. Why area 2A? Because this and this together. So we can say total area 2A. Then 100 minus 0. 100 minus 0. Length is same. So here the terms, this 2 and this 2 cancels. So we are getting 4KA into 100 minus 0 divided by L is there. Actually that is H second. Now we are taking the ratio for this now. So we can say, that is, suppose we are considering the picture now correctly. Please see, look. So H1 divided by H2 is equal to, what is H1 formula there? H1 we calculated 3K by 4L into A into 100 minus 0. So I am writing, that is 3K by 4L into A into 100 minus 0, 100 divided by, here 4K 100 by 0, it's L coming. So I can write that is equal to 4K A by L into 100. So you can cancel the similar terms here. Please be here. Now look, 100 and 100 cancels already. And we can say here A and A cancels. And here we can say K value and K value cancels. L and L cancels. So it's coming 3 by 16. The ratio is 3 by 16 now correctly. Okay, series to parallels. No, look, they are asking in the question, please dear. Look, that is the ratio of the heat current flowing parallel to that series. So ratio is reverse. So it is 16 by 3. So we can say the ratio is, here in the question they are asking, H second by H first. So that is equal to 16 by 3. 16 by 3. Important question. Important question. Please take care in this question. Here area is different. The last question that we are trying, look, this question, easy question, black body at a temperature 300 Kelvin, which is proportional to 300 raised to 4. Direct question will get, that is T raised to 4 is there. Now the next one, 540 gram of ice, 0 degree, mixed with 540 gram of water at 80 degree. Final temperature of the mixture is. So there is an important point I am saying. Look, the shortcut. If equal mass of ice and water are mixing, please listen here. If equal mass of ice and water are mixing, if the temperature of water is less than 80 degrees Celsius, then the mixture temperature will be less than 80 degrees Celsius. So without working you will get, look, if two equal masses, so we can say if equal mass of ice and water are mixing, if they are mixing, if temperature of water is less than 80 degrees Celsius, then temperature of mixture will be less than 0 degrees Celsius. Okay, second case, look, if in the same case, if temperature of water equal to 80 degrees Celsius, then temperature of mixture will be equal to 0 degrees Celsius. Temperature of mixture is 0 degrees Celsius. Next one, if temperature of water is more than 80 degrees Celsius, then temperature of mixture will be greater than 0 degree Celsius. Shortcut, please see the shortcut already. So I am repeating the last point once more. Please see, first of all, if equal mass of ice and water are mixing, if temperature of water is less than 80 degrees Celsius, then temperature of mixture will be less than 0 degree. In this question, look, 540 gram of ice, 540 gram of water, 880. So we can say temperature of water is 80. So temperature of mixer will be what? 0 degree Celsius. So right answer is option A. So I think this discussion actually for long term, this chapter is taking actually for 2 days. 2 into 6 hour, 12 hour theory, then practicing again. So that we are summarizing in 1 hour because it is crash. We have a very less days are remaining. So please prepared well. Questions are around you. Please go through the questions. Day and night is not a matter. Work correctly and make it perfect. I'm Shamim. Thank you.
Brilliant Qatar, your trusted coaching partner for IIT, JE, NEET, Science and Commerce tuitions with 10 years of excellence in quality training. Brilliant Qatar.